Designing a hash set looks like it needs a simple list, but there's a bucket enchaining trick that gives you average constant time for every operation. The problem asks you to implement a set of integers with 3 methods: add a key, remove a key, and check if a key exists. You cannot use the built-in hash set. You have to build the data structure yourself. For example, after adding 1 and 2, a contains call for 1 returns true, for 3 returns false. Adding 2 again does nothing. Contains 2 is still true. Then removing 2 makes the next contains 2 return false. The naive way is to keep a single list of all inserted keys. Adding means scanning the list to avoid duplicates, removing scans to find the element, and contains scans as well. Every operation touches the whole list in the worst case, so each runs in big O of n time while using big O of n space. That's too slow when the number of operations grows large. The key insight is to spread the keys across a fixed number of buckets using a simple hash function, then handle collisions with a linked list in each bucket. We allocate an array of, say, 1,000 empty linked lists. To add a key, we compute its bucket index by taking the key modulo the bucket count, then check that bucket's list for the key and append it if missing. Removing does the same bucket lookup and deletes the key from that list if present. Contains just checks the corresponding bucket's list. Because the bucket count is constant, the average list length stays tiny, giving us near constant time per operation. You'll recognize this pattern whenever you need fast membership tests and can afford a fixed size bucket array with chaining to resolve collisions. Average time complexity is big O of 1, constant time for add, remove, and contains, with a worst case of big O of n when all keys fall into the same bucket. Space complexity is O, n plus bucket count, because we store every key once plus the bucket array. Try the next problem, same pattern. Subscribe for more deep dives into data structure design.